Hello dear students, let's begin with the chapter 2, Valence bond theory of coordination compounds. In first term, you studied about Warner's theory and Sedgwick model. But you must have realized that the limitations of Warner's theory and Sedgwick model made it necessary to search for a new theory of bonding in complexes. Even Pauling, he realized that in his early model there were lot of defects. He observed that sometimes the number of orbitals needed for accommodating the electrons did not agree with the number of available orbitals of the central metal atom or ion. Sometimes the observed and expected magnetic moments of the complex did not agree. These and such other difficulties made Pauling to improve his theory, and then the theory was applied to complexes under the name valence bond theory. So, in this chapter, we are discussing VBT of coordination compounds. Before starting the assumptions of valence bond theory, I just want to revise the electronic configuration of some of the d block elements, because in coordination complexes the central metal ion is mostly from d block. And what are their electronic configuration and how electrons are written in box diagram, that we are discussing here. You can see here there are 10 elements from 3D series starting from scandium up to the zinc. Their atomic number, it ranges from 21 to 30, and the electronic configuration for scandium with atomic number 21, it can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. This electronic configuration, that is 1s2, 2s2, 2p6, 3s2, 3p6, this is the electronic configuration of noble gas argon. And you can see this electronic configuration is constant in all 3D series element. So simply in place of this electronic configuration, we can write down in square bracket argon, and the remaining electrons in s orbital and d orbital can be written like this. So the noble gas configuration of scandium, it becomes argon 4s2 3d1, and electrons we can show in box diagram as these are 4s electron, so 4s2, and these are d block electrons, so we can show here 4s2 3d1. For titanium, similar electronic configuration will be there, that is argon 4s2 3d2, and in box diagram it can be represented like 4s2 3d2. For d orbital, there are 5 suborbitals or 5 boxes are there, while for s orbital there is only one box. For vanadium, with electronic configuration 23, atomic number 23, the electronic configuration will become argon 4s2 3d3. For your understanding, you need to remember one point, that see here vanadium, its atomic number is 23. So how you can simply write down its electronic configuration like argon 4s. First write down 2 on 4s and then write down 3 on 3d. Like iron, its atomic number is 26. So how you can write down the electronic configuration? In a simple way, argon, on 4s you can write down 2 and on 3d you can write down 6. So it becomes argon 4s2 3d6. For nickel 28, it is argon 4s2 3d8. So in this way, from scandium to zinc, we can write down the electronic configuration by using noble gas also. But here if you observe, there are two anomalies. One is for chromium and another is for copper. Chromium, its atomic number is 24. So what electronic configuration we expect here? We expect argon 4s2 3d4, 2 and 4. But the actual electronic configuration, it is argon 4s1 3d5. So why the electronic configuration of chromium is different than the expected? The same is for copper. The atomic number is 29. So the expected electronic configuration, it is argon 4s2 3d9. But actually it is written as argon 4s1 3d10. So why these exceptions are there, or why these anomalies are there in the electronic configuration of chromium and copper? So let's discuss about this. Now first take the example of chromium with atomic number 24. The expected electronic configuration, outermost electronic configuration, it is 3d4 4s2. But the observed electronic configuration, it is 3d5 4s1. That means one electron is shifted from 4s2 to 3d4 and it becomes 3d5. The same is observed in copper, whose atomic number is 29. The expected configuration is 3d9 4s2. But the observed configuration is made by shifting one electron from 4s2 to d orbital and it becomes 3d10 4s1. This happened because the half-filled orbitals and completely filled orbitals are more stable. To achieve the more stability, the electronic configuration from chromium, it is converted from 3d4 to 3d5 so that it has half-filled d orbital, and in case of copper, it is changed from 3d9 to 3d10 so that it can has completely filled d orbital and hence it can achieve the more stability. So the copper and chromium, they have exceptional configuration. Now see here how the electrons are filled in d orbitals. In scandium, it is d1, so it is only one electron. Then there are two electrons. In vanadium, there are 3 electrons, so 1, 2, 3. In case of manganese, the outermost electronic configuration is 4s2 3d5. So electrons are 4s2 and all 5 suborbitals or blocks are filled first. Once all the 5 boxes, they get 1 electron, now the pairing will start, and when we go towards iron, whose atomic number is 26, so it has 4s2 3d6. 4s2 3d6. So it becomes 2 electrons are filled in 4s, and then for 3d6, first all 5 suborbitals, they are given 1 electron each, and the 6th electron is paired here. D7, again 1 electron is given to each, and then next 2 electrons are paired in this way. So in this way the electrons are distributed in d orbital. Now see here, these are the box diagrams of the electronic configuration of d block elements starting from scandium to zinc, which we have already discussed. Now when ions, its electronic configuration is expected. For example, see here V3 plus. The actual electronic configuration of vanadium 23 is argon 3d3 4s2. But when we want to write down the electronic configuration of cation V3 plus, that means 3 electrons are removed. So how we can remove the electron? We need to remove the electron first from s orbital and 1 electron from d orbital. So what will be the electronic configuration of V3 plus? It is just argon 3d2. Now if we write down Cr3 plus, so that means we need to remove 3 electrons. So first remove the electron from s orbital 1, and remaining 2 are from d orbital. So now what will be the electronic configuration of Cr3 plus? It is argon 3d3. Let's see Ni2 plus. Nickel atom, its electronic configuration is argon 3d8 4s2. If we want to write down Ni2 plus, that means we need to remove 2 electrons. Always remember, first remove the electrons from s orbital and then remaining electrons from d orbital. Here for Ni2 plus, we need to remove only 2 electrons, and those 2 electrons we can remove from s orbital 4s. So what is the remaining electronic configuration? It is argon 3d8. Take the example of Mn2 plus. Mn2 plus means 2 electrons we want to remove. So see here Mn. Remove these 2 electrons from s orbital. So what will be the electronic configuration of Mn2 plus? It is argon 3d5. So in this way we can write down electronic configuration of atom as well as its ions. Now, why the hybridization is required and how it decides the shape and relative strength of bonds. So this part we will discuss in the next video.